Have you ever wondered where the incredible power for a nuclear reactor comes from? It all starts with uranium, a heavy metal found deep within the Earth. For most of history, uranium was just another element, until scientists discovered the immense energy locked inside its atoms. Uranium ore is mined, crushed, and processed into a yellow powder called yellow cake, the first step in its transformation. What makes uranium special is its radioactivity. Its atoms are naturally unstable and release energy as they decay. But on its own, this process is slow and weak. The real breakthrough came when we learned to trigger a chain reaction, splitting uranium atoms to unleash massive heat. This heat boils water, creates steam, and spins turbines, generating electricity for millions. Uranium is more than a metal. It's a cosmic battery, charged since the birth of our solar system. By harnessing its properties, we've turned a simple rock into one of the world's most powerful sources of clean energy. The journey from ore to electricity is a testament to human curiosity and ingenuity. It all begins with a rock and ends with lighting up our world. Next, let's see why natural uranium needs a boost before it can power a reactor. Not all uranium atoms are the same. They come in different versions, or isotopes, mainly U-238 and U-235. U-238 is the heavy common isotope, over 99% of natural uranium. U-235 is rare, making up just 0.7%. U-235 is the key. It's fissile, meaning it can easily split and sustain a chain reaction. U-238, on the other hand, absorbs neutrons and stops the reaction. With so little U-235 in natural uranium, it's like trying to start a fire with mostly wet logs and only a few dry twigs. To power most reactors, we need more U-235, so we use a process called enrichment. Enrichment increases the U-235 concentration from 0.7% to about 3.5%, making the uranium suitable for reactor fuel. Without enrichment, most nuclear power plants couldn't operate. But how do you separate two nearly identical atoms? Let's go inside a gas centrifuge. Separating U-235 from U-238 is a huge challenge. They're almost identical in weight. The solution? The gas centrifuge process. First, uranium yellowcake is converted into a gas, uranium hexafluoride or UF6. This gas is spun at incredible speeds in tall centrifuge cylinders. The heavier U-238 molecules move toward the outer wall. The lighter U-235 molecules stay closer to the center. Each centrifuge makes only a tiny difference, so thousands are linked in a cascade, gradually increasing the U-235 concentration. The result? Low-enriched uranium, LEU, ready for fuel fabrication, and depleted uranium left behind. It's a remarkable feat, separating atoms by harnessing pure speed and precision. Now let's see how this enriched uranium becomes the fuel that powers a reactor. Low-enriched uranium gas isn't ready for a reactor yet. It must be turned into a solid. The gas is converted into uranium dioxide powder, then pressed into tiny, energy-packed pellets. Each pellet, about the size of a fingertip, can produce as much energy as a ton of coal. The pellets are baked at high temperatures to make them dense and durable. They're loaded into metal tubes, fuel rods, made from strong neutron-friendly alloys. These rods are bundled into fuel assemblies, each containing hundreds of rods. A reactor core holds many assemblies, ready to generate clean electricity for years. From gas to solid, the process creates a high-tech, energy-dense fuel. But why is enrichment such a marvel of science and engineering? Uranium enrichment is a quiet marvel, turning a common element into a powerhouse of clean energy. It's the critical link that enables efficient, large-scale nuclear power without greenhouse gases. Gas centrifuges, spinning in perfect harmony, showcase human ingenuity and precision. The result, a fuel assembly that can power a city for a year, unmatched by other energy sources. Enrichment also allows us to tailor fuel for different reactors and research needs. By controlling U-235 levels, we ensure safe, steady, and reliable power. Ultimately, enrichment is a gateway to a cleaner planet, reducing fossil fuel use and fighting climate change. It's a story of curiosity and innovation, unlocking the universe's hidden energy for humanity's benefit. As we improve these technologies, we're building a brighter, more sustainable future, all powered by the incredible energy hidden within the atom.